All right. So good morning, everyone. Welcome to the CE seminar series. I'm serving as host of ceremony, replacing Dr. Soraneni, who cannot be with us today. And I have the pleasure to introduce you Dr. Xianming Shi, the new chair, professor and chair of the Civil and Architectural Engineering Department here at the University of Miami. Dr. Shi comes from Washington State University, where he previously served as professor and chair. A little bit about his interest, material science for circular economy and for construction, preservation and resilience, mainly focused on transportation infrastructure, durable, sustainable, and smart pavements, uh, also construction of smart cities and sustainable built environments, an expert on material science and with a lot of, I would say, applications towards what we're doing here in Miami and the general interest around coastal and resilient cities like Miami. Today, he's going to talk to us about nanotechnology, enable sustainable and durable concrete infrastructure. Dr. Shi, welcome, and it's all yours.
Thank you so much, Landolf. Can you hear me all right? Okay. So, good morning, everyone. Today, I'd like to share with you a topic I feel quite blessed, with over the last decade. We've done quite a bit of work in this domain, which is nanotechnology enables sustainable and durable concrete infrastructure. This is a really broad topic. So what I'll share today within 45 minutes will be mostly work we've done in the last 5 to 8 years. Again, my name is Xianming Shi. I'm a professor and department chair at the University of Miami for the Department of Civil and Architectural Engineering. And the first question in mind is, concrete seems so taken for granted, so mundane, can we make concrete durable? Because we often see cracks and premature failures. But if you look at what the Romans did, the Colosseum still standing after 2,000 years. So there's something to it we don't fully understand, apparently. Of course, back then the cement chemistry was different. They didn't use steel rebar and so on and so forth. One concept that I often introduce when I start teaching concrete durability class to my students is that you should see concrete as a living material, a solid sponge, not a piece of rock, because it does, breathe in and breathe out moisture and other ionic species or whatnot. And it does degrade over time. It's a living material. It interacts with its service environment. So if you think as a solid sponge, it's a multi-scaled simulation could be done in terms of how different pores or air voids interact with cement paste and aggregate and rebar. They're all at different length scales, and it's getting very complicated. Even though it's supposedly it's a very cost-effective material, but it's a very high-tech material, I would argue. And one interesting thing is in the last 3 or 4 decades, especially, there's emerging technology such as nanotechnology. If we put concrete as a composite material under that sort of lens, we're talking about, okay, if you look at this chart, on the x-axis is the particle size, the y-axis is the specific surface area. And you can see that coarse aggregates are way over there towards the right, and at the bottom, that means it has high particle size but low specific surface area. But if we look at the other end of the spectrum, say nanocarbon, for instance, today I'll talk quite a bit about graphene oxide, which is one type of nanocarbon. Then you were talking about the size of between 1 to 5 nanometers, and then a surface area which is 1 million square meter per kilogram, which is really high. So with that kind of high specific area, the property or behavior of the material changes significantly. So that's where the magic occurs, because this type of material tends to have really high surface activity, and therefore, the interaction between the nanocarbon with cement particles and water will be dramatically different than how a coarse aggregate would interact with cement and water. So today I try my best to share some of the recent studies, starting from a graphene oxide enabled flash-based geopolymer, which is a patent technology we developed at Washington State University. And then, of course, I move on to some other graphene oxide enabled innovations. Just to give you two examples. One is how we can better use silica fume, yet another industrial byproducts. In this case, silica fumes from the semiconductor industry, and flash is from the burning coal to produce electricity. And then also another case was how we could upcycle waste masks into divert them from waste stream towards beneficial use in concrete. And then I'll talk about some other nanotechnology-enabled innovations, which may not be exactly graphene oxide. For instance, we talk about nanosilica, nanoclay, and things of that nature, and then conclude. This is a little photo we took in my previous lab where we were doing some work on carbon negative concrete. Again, nanotechnology was also a key component to that technology, which is now patent pending, and we even launched a startup company, and even the company already got some SBR grants. So starting on from the first topic, graphene oxide enables the clinker-free concrete based on coal fly ash. As you can see, we made some previous concrete cylinders in the lab. The two on the left were made with ordinary Portland cement. The two on the right made with coal ash without any sort of cement clinker. And the color is slightly different. Other than that, most behaviors are pretty much comparable. I mean, in terms of mechanical properties and durability, as you will see later. So taking one step back, why do we do this? Well, on the left-hand side, you can see that the cement production arguably is responsible for, well, some say 5%, some say 80% of global CO2 emissions. But anyway, it's a large footprint. But on the right-hand side, you got this underutilized industrial byproduct. Again, from burning coal to produce electricity, we have a lot of ash, fly ash or bottom ash. You see this picture where if the fly ash is being underutilized, then there's a risk of air pollution. On the bottom right, there's also the risk of contamination of the land resources when there's a heavy rainstorm or some sort of event. Now, we're switching orders here. On the bottom left, you see, again, yet another place, basically is a huge pond with the unused fly ash. And oftentimes, if it's not done properly, this could be a contamination source of the groundwater. And as you can see, the numbers in the US, roughly annually we produce about 36 million tons of fly ash, and only about 55% were utilized. I believe the numbers are improving in terms of utilization rate because of the R&D and the implementation of some of the novel solutions. So graphene oxide is a carbon-based nanomaterial. I'm sure some of you have heard about graphene, which won the Nobel Prize about 2 decades ago. Graphene is made from graphite, usually either through a physical approach or chemical approach. The chemical approach we took is known as modified Hamer's method. Basically, you use strong acids to exfoliate the nanoplatelets out of this graphite material. And in the process, because of the strong oxidation, the nanoplatelet surface would have functional groups, such as hydroxyls, carboxyls, as revealed by the FTR on the left and the XPS on the right. So you got these functional groups, which are very beneficial because they make the graphene oxide reactive. So that's one thing different between, graphene oxide and carbon nanotubes. Graphene oxide has actually more functional groups. They're more reactive, more compatible with water and other polymer matrices. We've done quite a bit of work in terms of putting graphene oxide a trace amount in asphalt materials, in coatings, but that's not part of the talk today. today we focus on the cementitious materials. So you can see that this graphene oxide is actually water soluble up to about 5 grams per liter, and all the way up to 10 grams per liter, you can still make a very stable suspension, aqueous suspension. So what I call as a duck ink. So with this duck ink, if you dry it under the microscope, you can see that, again, they're like crumbled papers. If you take a piece of paper, say 11 by 8.5, and crumble it into a lot of wrinkles, and then you shrink it by 1,000,000 times, that's roughly the size of a graphene oxide nanoplatelet. So we can see that under the scanning electron microscope, very clearly there are wrinkles. These wrinkles actually make them feature certain types of properties that may be very desirable. Actually, wrinkles are good for us. Now, certainly my group was not the very first one, studying how we use this kind of unconventional concrete admixture in concrete, but we were probably the first one to reveal some of the mechanisms, how they actually work. This is a multifunctional role. Multifunctional admixture. When graphene oxide is applied at 0.02% by weight of cement, for instance, in this case, this paper focuses on the fundamentals. So it's not a real concrete system, it's a cement paste. You can see 0.02% increase the 28-day compressive strength of the paste by about 29%. And on the mechanism side, we reveal that the graphene oxide basically is more than just a nanofiller. It improved the hydration degree of cement and the polymerization of these hydration products. And also, because they're negatively charged on the surface, again, imagine really strong, mechanically strong, and even thermally, well, I take back the thermal part. The thermal part is, if we reduce the graphene oxide, remove some of the function groups, then we can make it thermally and electrically conductive. That's a different story. But graphene oxide itself is not thermally or electrically conductive. But the negatively charged, they consume the calcium cations in the juice. Again, going back to the concrete being a solid sponge, when it's partially or fully water saturated, you basically got this highly alkaline juice in the so-called the concrete pore solution, and you have calcium ions. And because of this interaction between the negatively charged nanoplatelets and the calcium cations, and some other actually negatively charged ions, then you induce different kinds of hydration products, such as tobermorite-like hydrates or ginite-like hydrates. So these mechanisms were revealed using a lot of different tools. I won't go into details here, but again, graphene oxide is a magic multifunctional admixture for ordinary potent cement concrete systems. So we can actually see the nanoplatelets under the microscope. We see the strength improvement, and also we see improvement in durability. But now, earlier I mentioned, the specific surface area, but look at this one. If we go by the same unit, cubic meter per kilogram, then we're talking about 2.6 million, which is even higher than that 1 million number we mentioned earlier on the graph. And the zeta potential is another parameter to watch out for, because not all the graphene oxides are made the same. So the amount of negative charged groups on the surface is measured typically by zeta potential at a neutral pH. So in this case, this kind of zeta potential minus 30 millivolt indicates this is a somewhat stable system, and it's about 1 nanoplatelet, instead of multiple. Because when you have more than 5 nanoplatelets sticking together, then that graphene oxide is not very useful. It's more like a micromaterial than a nanomaterial, partially because it's the loss, basically loss of its magic once you have more than 5 nanoplatelets sticking together. So the question then becomes, can we manufacture a concrete without any cement? So we were playing with this Class C ash, which is, fly ash. Typically, the classifications include Class C, Class F, and Class N. Class N stands for those naturally occurring. But for the industrial byproducts, class C, it stands for those tends to have higher calcium oxide content, and class F is those with higher silicon oxide content. So this class C ash, without any activator, when we mix it with water at the water ash ratio of 0.3, you actually get some strength. That's the figure on the left. You see that these fly ash particles have the unique spherical shape, so can you easily identify them under the microscope. This is a really fine scale, right? If you look at this chart, it's probably 25 by 25 micron, which is much finer than your hair. So what's fascinating is that your human hair typical diameter is 80 microns, which is 8,000 nanometers. And the phenomenon occurring at this scale, 25 to 25 by 25 micron scale, actually affect your engineering performance of the material. So you can see on the right-hand side, without activators, so 28-day compressed strength is about 20.5 megapascal. But when we add water glass as one of the activators, I think in this case, we also added calcium chloride, then you see further dissolution of these spheres on the microscope. That's a figure on the right. So these are scanning electron microscopes. And you induce formation of additional hydrates, which provides additional strength and durability for this concrete. So that's all good. And then a backscatter electron microscope reveals even more information, because in addition to morphology, the color, the brighter constituents indicate a heavier element. So this also not just morphology, but also some hint of the chemistry. Now, here with a little bit activated, we can get to 34 megapascal-ish, which is roughly 4,000 psi, but we want to go further. So by adding the 0.02% green graphene oxide by weight of ash, we can increase another, roughly speaking, 25%. So you can see here these improvements by the trace amount of graphene oxide in this activated fly ash paste, at 7-day, 14-day, 28 days. So now we're reaching approximately 6,000 psi at 28 days. So again, this, the fundamentals, why things are happening this way. And what's interesting on the right-hand side, I want to show you is, you compare these on the left. We have got 3 cylinders, right? The one made with cement is on the left, and the one with active flash is on the right. That's a little bit concerning because they're staining, right? That means some of the water glass alkali is leaching out, even though we're not using any sort of sodium hydroxide, because most geopolymers would either, typically use heating or a mixture of sodium hydroxide and water glass. But in this case, we didn't use that. But even though we have much less use of the alkali, still this alkali leaching. But when you add graphene oxide, the one in the middle, you see the leaching stopped. So the surface is pretty smooth. This indicates that the 2D nanomaterial, the nanoplatelets we're talking about, has this wonderful ability to encapsulate the alkali. And this could be extended to encapsulation of heavy metal or other pollutants. Actually, even for nuclear waste, right? We know nuclear waste typically is contained using concrete, but now this type of 2D nanomaterial will further enhance the ability of concrete to encapsulate and contain the pollutants, keeping them from leaching out at a faster rate. So going back to fundamentals, what happened there is if these are silicon nuclear magnetic resonance or NMR spectra at 56 day. And if you look at the one on the left is the one geopolymer, in other words, activated fly ash without adding any graphene oxide. But once you add graphene oxide, even though at 0.02%, the hydration products change significantly. Of course, this is a very busy chart. What I'm trying to show is that the silicon or silicate in the hydration product takes many forms, from Q0 all the way to Q4. And typically for ordinary Portland cement concrete, the silicate exists in the form of Q1, Q2, and Q0. Q0 basically is unhydrated cement clinkers. And Q1, Q2 means like there's one or two neighbors who happens to be also silicate or silicon atoms. So, but once they have more network structure, more neighbors being silicon or silicate, then you're moving into the domain of Q3, Q4. I would argue that when you have more than 50% Q3, Q4, then it's truly a polymer or geopolymer instead of a linear polymer, which is a CSH gel or calcium silicate hydrate. I know the cement chemistry is a little bit confusing because here in cement chemistry, C doesn't stand for carbon, it stands for calcium. S stands for silicate, and H stands for hydrate. So it's a little bit different how we view the chemistry from high school, I guess. But this is a very busy chart, but the main storyline is that with a trace amount of graphene oxide, you actually change the hydration products and make it quite different. The numerical numbers are here. So basically, you see more, I mean, again, the total peak area under Q3, Q4 is increased from 47% to almost 55%. So in other words, this indicates an increase in the polymerization degree. And this kind of network structure, or higher degree of polymerization of the inorganic material, translates to better resistance to chemical attack, such as resistance to deicers or sulfate attack or acid attack. So now we actually could use different tools to shed light on different pieces of the puzzle and reveal the whole picture. For instance, on the left-hand side is the NMR results showing the graphene oxide reduce the Q2 type of silicate. And on the right-hand side, this is a TGA or differential TG. And basically, they collaborate and tell the same story. Now, there's another tool we use, which is EPMA or electron probe microanalyzer. So for instance, here you take a small cross-section of the concrete, or in this case, mortar, and then you select an area, let's say 100 by 100 microns, and then you scan it once, you get at least 5 or 6 different elements. Here we'll only show 2, which is calcium and silicate, but we would be also interested in sulfate, aluminum, iron, and so on. So this is a color map. The red color indicates a higher concentration. So these are actually digitized. So 100 by 100 micron area would give you 500 pixels times 500 pixels. So it's, tens of thousands of data points. So you can do color mapping of the elements, which is very visual, or you can do the elemental ratio by dividing calcium to silica. Then you can create another sort of map. So again, visually, you can see some difference from the top one, which without graphene oxide, the bottom one with graphene oxide. But there are other ways. For instance, quantitatively, like I mentioned, we have tens of thousands of data points. Then you can calculate the aluminum calcium ratio as a y-axis, silica to calcium ratio as x-axis. Then you start seeing some patterns. For instance, the one on the left without graphene oxide, the one on the right with graphene oxide, you see this ginnite-like material showing up in this corner. So, and again, in the case of flash-based geopolymer, it's not just CSH gel, it's actually more like CASH gel. A stands for illuminate. So again, we have different tools to shed light on the same story. Again, NMR, EPMA, and this one, EPMA can also scan through. I mean, EPMA has different modes, like under the BSE or backscatter electron mode, you can have this image, and that seems to indicate a ginnite particle. And then you scan you do the 1D line scan on the surface, and you can see the richness of the carbon, which indicates, okay, sorry, where's carbon? Okay, carbon's here. Compared with the adjacent area, the carbon's a little higher. That means, okay, you got some graphene oxide here, most likely. And then you see some other elements. So all the different data points eventually converge and tell the same story. Now you got more graphene oxide induced ginnite phase. Similarly, we also found low quartz, which is a Q4 type of hydration product. And again, different tools shedding light on the same story. So in summary, what is the function of the graphene oxide? Again, these are carbon-based nanomaterial like a platelet, but on the surface with a lot of a lot of functional groups like carboxyls, hydroxyls, and so on. So the negative charge, so they exclude the intermediates. These are typically calcium cations, and they consume some of the so-called network modifiers. These are typically silicon tetrahydrons and I got other consume the network modifiers, which are the calcium cations, but they exclude the intermediates, which are typically aluminum tetrahydrons, which are negatively charged. But the silicon tetrahydrons, most of them don't have any charge, so they're not affected. So if you look at the chemistry, the cement chemistry versus the flash, they have some similarity. So that's the basis of our original motivation of activating the ash to generate a cement, I would say, clinker-free green cement. So the main story here is we're trying to divert an underutilized industrial byproduct of waste towards beneficial use, to partially, actually to fully replace cement in concrete. So the first one is the flash is the inorganic polymer, so you have to dissolve it. So we use activators such as waterglass and calcium chloride to help dissolve it. Now, once it's dissolved and reacts with water, you form the new gel. Because of the presence of these nanoplatelets, they're like coaches. I would say originally without graphene oxide, it's like a soccer field with random players. Now with coaches, they're more organized. So they're reorganized into teams, and the final product is much higher degree of polymerization and more regulated microstructure. So now that's basically the pattern itself is to develop a clinker-free cementitious binder from flash particles, flash industrial byproduct. Now, of course, you may ask a question about cost, right? Nanotechnology always there's a concern. Cost-wise, 10 years ago, it's ridiculous, right? Like graphene oxide was sold at $100 per gram. But not to my surprise, things change. And because of economy of scale, now you can get graphene oxide, really high quality graphene oxide, $175 per pound. So when you do the life cycle cost analysis, you'll find this is actually pretty cost effective. So with this greener cement, I would call it the geopolymer, then we try to put it to use. So the first field demonstration we did was a pervious concrete. Pervious concrete, for some of you already know that it's a very good tool for low impact development because of many environmental benefits, such as the ability to allow rainwater to infiltrate through. So you recharge the groundwater in areas which are arid, well, not in Miami, right? In Miami, we have probably too high a water table, so we need some change to that design. But in many other areas, recharging groundwater is pretty important, purifying the stormwater, reducing the traffic noise, reducing heat island effect, and also even reducing slip fall risk when in cold regions when you have like black ice or light snow. So there's a lot of greenness in this pervious concrete pavement compared with the traditional impervious pavements. One thing that's not very green is we still use cement, right? So that's where we're trying to replace the cement. So again, here we develop 4 types of mixed designs of pervious concrete. One use cement, one use cement with the graphene oxide, one use activated ash, one use ash plus the graphene oxide. Typically, the design is different than in pervious concrete by reducing or eliminating the use of fine aggregate. So you've got the built-in ability to infiltrate rainwater. So the gist of the story is that, yeah, if you look at the density, the somewhat denser, I mean, the flash ones versus the cement-based ones, but they're still pretty reasonable. And then their void ratio is in the range of what we would define as pervious concrete. And in terms of compactability or workability, they're very similar. So when we look at strength, yeah, again, especially with the graphene oxide group, is basically comparable to the group with graphene oxide modified cement pervious concrete, even though the color is a little different. Again, they fall into this empirical range in terms of relationship between split tensile strength and compressive strength. So they're basically, reasonable rivals. So when you look at Young's modulus and so-called degradation resistance or abrasion resistance, again, the flash based pervious concrete actually has a somewhat higher Young's modulus, but when you look at the resistance to abrasion, they're pretty good. I mean, especially with one modified by graphene oxide. So these are very promising results. And when we also did the durability, right? Because it's not always just about mechanical properties or physical properties, but also durability in the long run. So here we look at the application scenario in the cold regions. Of course, this experiment, as we know, STM C666 is unrealistically harsh on the concrete, especially in the case of pervious concrete, where in real environment, it's highly unlikely you would have pervious concrete sitting in a pool of de-iced water, right? Because they will infiltrate down into base and subbase. But in this case, since we didn't have another method, we took this method, and it's pretty unrealistic, harsh. But the main storyline is that with the modification of graphene oxide, the flash geopolymer did comparably well as the cement-based ones. Now, what about de-ice? Sorry, that one was freestyle, so no de-icing involved. But again, still very harsh because they were sitting in water, and the freezing rate is very rapid, which almost never happens in the real field environment. Now, in the ISO situation, actually the one with geopolymer and graphene oxide did better than the OPC counterpart. And there's, of course, some chemistry explanation because the graphene oxide improved the resistance of the paste to combination during the salt scaling. And again, I won't go into details. All these are published in ACI or other journals. So, so this specific work, basically our contributions are as follows. We demonstrated the beneficial use of mixing 0.02% graphene oxide in OPC and in flash geopolymer paste, mortar, and concrete. They increased the compressive strength significantly, and more impressively increased the 7-day, 28-day compressive strength of geopolymer paste concrete by more than 50%. NMR shows that they improve the polymerization degree, and they also regulate the type of hydration products that would form, and especially favor those with better strength. And there's more mechanisms revealed. So with that, moving on to some other, graphene oxide enabled innovations. So there are 3 of them, but I probably only have time to talk about 2. The first one is utilization of silica fume. It's nothing new. Silica fume has been a very popular supplementary cementitious material, just like blast furnace slag or flash. But silica fume is a byproduct from semiconductor industry, and we found a way to better use silica fume by treating it first with graphene oxide. Again, the dark ink I was talking about. Second example is during pandemic, it inspired us to find a way to beneficially use single-use masks. So we were able to treat these mask-derived microfibers with this dark ink, and then got some really interesting results. Now we're extending this line of research towards recycling or upcycling waste clothes. And the third one, I won't have time to talk about, is a penetrating sealer for concrete protection. And that also involved the combined use of graphene oxide and nanoclay. So starting from the first example, silica fume. The challenge we ran into here was the silica fume surface is negatively charged. So we cannot easily use graphene oxide, which is also negatively charged, to treat its surface. How we make that happen is we actually treat it first with alkali, so that, calcium hydroxide solution, so that we make the surface positive charge, and then we treat it with the dark ink. And then the main results are pretty fascinating, because again, the use of the graphene oxide is only 0.04%, but the modified silica fume is about 5%. And then in this case, you improve the 3-day, 20-day compressed strength by 56% and 29% respectively, compared with the 5% silica fume without the graphene oxide treatment. So again, it's a significant improvement, but what's even more interesting is this kind of approach reduced the water absorption by about 33%. So the water absorption basically is an indicator of how fast water gets into the concrete. Again, we're talking about a solid sponge here. And one thing we also did is the characterizing the microstructure of this solid sponge, so to speak. The y-axis is the pore volume, the x-axis you can see the 4 different groups. Basically, the story is that with the pre-treatment of silica fume by graphene oxide, you basically increase the amount of finer pores, which are smaller than 100 nanometers, and reduce the larger amount of larger pores. So that's very desirable for better durability. And then again, we did an NMR, which shows that increased polymerization degree, and also the chart at the bottom shows that if you move from the right towards the left, then you are seeing increased compressive strength and also reduced porosity overall. Again, the details of porosity are the top figure, where it shows finer pores increase and larger pores decrease. So moving on to another example is medical masks, right? This story actually, even though it's a tiny amount of work we did publishing one single paper, but it got a lot of attention. Supposedly they tracked it down and reached about 50 million viewers and across dozens of countries, different languages, and so on. So the idea is very simple, actually. As you can see here at the top, once we remove the cotton, the metal, and then you got this polypropylene mask, and use a home style. Well, you first cut it and then use a home style blender, and then you can break it with the help of the liquid. You can break it into fine, microfibers, which are the size of your hair, roughly speaking. So 40 microns in diameter, typically, for instance, or 20. So when you put that into concrete as some sort of fiber admixture, I would say, the compressive strength reduced a little bit because these are polymer fibers, but it's not too much of a concern. You're losing about 3% of the, this dark ink extruded fiber, you're losing 3% of the compressive strength, but you're gaining 47% of the split tensile strength, which is pretty impressive, especially considering this material is very cheap. Now, we also look at how it does in terms of freeze-thaw durability. You can see the dosage was 0.02% graphene oxide by weight of the cement, and the polypropylene microfiber, which is recycled from masks, is only 0.1% by volume of the concrete. And overall, the graph on the left shows mass loss. The graph on the right shows compressive strength loss over the number of rapid freeze-thaw cycles. And in general, these kind of fibers help reduce the freeze-thaw damage. And we translate that to stochastic modeling. So again, the blue curve shows, right, it's significantly more number of freeze-thaw cycles it can endure compared with the ordinary Portland cement, or compared with just the mask fiber without the dark ink treatment. So I won't go too much into these details, but we also look at why it happens. Again, you see some sort of fiber pour out, this fiber pour out consuming some of the fracture energy. This also, when the fiber pour out, you generate some macro cracks, which also consume some of the fracture energy. And also fiber bridging, as we know, is another mechanism to mitigate the freeze-thaw damage or the tensile stress buildup during freeze-thaw cycling. So what's interesting is also when you treat the fibers with this docking or graphene oxide, the cement chemistry changes. Again, well, I should say the hydration products near the surface of the fiber is different than without the graphene oxide treatment. So, for instance, especially for the calcium and aluminum, is significantly different if you look at the box plots. And then, of course, another way to look is the elemental ratio. So, to summarize, there are numerous used masks littered or landfill without any treatment and or proper disposal, often they end up in the environment, causing a risk to aquatic species. And we demonstrate one beneficial use of such medical masks and illustrate great potential to upcycle them in concrete and help incentivize the collection of such masks. Of course, you know, I'm not in the business of doing this. I know there's a small company in Canada which are already collecting medical masks and diverting it from waste stream towards beneficial use. That's almost concurrent to our work. I'm not sure whether they actually read our paper yet. So there are a few papers published, but like I said, we're extending this line of research towards beneficial use of waste closures. That's a lot. So a little break, and then I'll move on to this, you know, the remaining time. So let's see, we got a little bit maybe time. So the last part is other nanotechnology enabled innovations. I talked 2 examples. So again, there are so many examples, but I'll only focus on 2. The first one is you can use graphene oxide to engineer the interfacial transition zone on the fine aggregate. Actually, more recently, we even on the coarse aggregate. So the way you do it is you treat the sand or rock, and then with that docking, and then put it into concrete, and then that works like magic. That's another pattern we found. And then another one is high strength ECC or engineered cementitious composite, also known as bendable concrete. In this case, we incorporate nanosilica to enable better self-healing behavior because we keep the cracks really, really fine, less than 30 microns in diameter, in width typically. And then, of course, other nanotechnologies like carbon negative concrete, we started this line of research. And then there's one of the secret ingredients is deposition of nanocarbonates on the surface of biochar. And we were able to push the envelope dramatically. Prior to our work, people usually use 1 to 3% biochar by weight of cement in concrete. And we were able to push the envelope all the way to 30%. So now we're talking about engineered biochar being a new generation of coal ash or supplementary cementitious material. And also, based on the life cycle assessment, we can say, especially with carbon negative concrete, the infrastructure could serve as part of the climate solution. But again, I won't have time to get into details, plus there's some IP issues, so I won't be able to share too much. Now, also we used wind turbines or other airplane at the end of life, recycled composite materials. Again, we treat it with some nanomaterial and put it into concrete. That's why we consider it as upcycling, because they do improve the properties and durability of concrete, not degrading them. Also, another one we did was externally bonded CFRP fabric to retrofit concrete. Our focus was nano-engineer the resin to make them more durable. Again, start from this. Actually, this is one of the patterns in review. Is we can treat this the sand with dark ink and then dry it, put it into concrete. You can see the results here on the top. Compressive strength, fracture strength both improve. Especially impressive is if you just mix the graphene oxide directly into fresh concrete, you get 20% or 11% in those compressive fracture strength. But if you actually use this new method, you get significantly better results. So you can see our work is standing out compared to many other studies out there in terms of better improvement in the strength and slightly lower usage of graphene oxide. So again, graphene oxide serves many different roles. Again, we use mercury intrusion porosymmetry to understand what happened. Basically, we're seeing, we're seeing more finer pores. And you see improvement in strength and reduction in porosity. And also under scanning electron microscope, we can see that the interfacial transition zone on the surface of the sand, in this case, is actually densified and become narrower. So, and again, we understand, this is a nanomaterial, so they're actually intact with cement paste, and the cement hydrates chemistry changed. So there's more details, but one thing I want to point out is like the cracks have become finer, and when it heals itself, this beautiful hydration product forms. I think it's a carbonate. Now, yet another example is the high strength engineered cementitious composite incorporating nanosilica. We use a high strength PE fiber, 2% by volume, and then you can get to a compressor strength more than 80 megapascal or 28 days. And then you typically get between 4 to 6% tensile strain. So it's a strain hardening composite material, especially the reference M2 use more flash than cement. So you can consider it as a high volume flash concrete with 0.5% nanosilica. The behavior is further improved. Again, I won't have too much time now, but improve the first cracking strength, tensile strength, strain capacity, everything, and you get more cracks, but finer cracks. If you look at the dashed blue line, this is the better behavior because most of the cracks are finer than 30 microns in width. So that makes it easier to heal itself when it goes through wet dry cycling, and that's proven. And then we can see the healing product is also different. When you have wider cracks, mostly it's calcium carbonate, but when you have finer cracks, your healing product is mainly CSH gel. So to conclude, nanotechnology holds great potential in transforming concrete as a composite material. I would consider there are two thrusts. One is nanoscience, truly understanding what's going on, at that fine scale, achieving mechanistic multi-scale understanding. The other is armed with such fundamental knowledge, then you can do nanoengineering. For instance, I talked about how the nano modification enables better geopolymer concrete, carbonate concrete, and again, most of it has something to do with interfacial engineering. And very last slide is my work over the last decade or so has been devoted to, of course, reducing the lifecycle cost and footprint of concrete infrastructure. But at the center is really nanotechnology. And at every stage of the life cycle, we've done something, whether it's mixed design or, decarbonization, all the way to retrofitting. With that, I welcome your questions.
Thank you. Very interesting and detailed presentation. Let's see. We do.
Oops, somebody said cannot see my screen. Was that the case?
No, I didn't receive it. I mean, I didn't have an issue, and I don't think that was an
okay.
issue.
But anyway, I can share the slides afterwards as a PDF. I mean, no problem with that. But any